Hello student, welcome back. This is the fifth video, okay, on chapter electrostatic, first unit. Clear? So as we have learned in the previous video about electric flux and torque, okay. So in this video, we're going to learn a very important topic for your exam, Gauss theorem and its application. Clear? Now see, what's Gauss theorem? According to Gauss law, the total electric flux uh, through a closed surface. Always remember one thing, student. When you come across closed surface means your 3D surface, 3D structure. Clear? Three dimension is equal to 1 by epsilon naught time of that net charge enclosed within that surface. Simple. Look here. So this one surface, closed surface, these are electric field line passing. Clear? So electric field line passing, right? So what will be there when electric field line pass through a surface means electric flux. We have seen in the previous video. So that electric flux, this electric flux will be equal to what? Your charge by epsilon naught. Charge by how much charge is there, right, in this, right? In this closed surface by epsilon naught. So this Gauss theorem. This is what? Gauss theorem. Is it clear? See? And this is a formula. This is already wrote here. Phi, sorry, yeah, phi electric flux, right, is equal to charge by epsilon naught. What's epsilon naught? We have seen in the second video. It's called absolute permeability. Okay, it's called what? Your absolute permeability of free space, and its value how much? 8.854 10 to the minus 12. So what's Gauss theorem? Always remember one thing. Gauss theorem means the electric flux is always equal to the charge on that particular surface by epsilon naught. By epsilon naught. Clear? Now remember one thing. If you've seen your notebook, there's some one proof about Gauss theorem, right? Clear? Uh, so let me do that proof. Okay. Suppose this one closed surface. Clear? Fine. So closed surface at the center I'm taking, this is the origin O and this plus charge here. So what do the plus charge do? They give out the electric field, right, in outward direction. So electric field I'm drawing this side. Clear? Fine. Now student, always remember one thing. This, as we know the plus, we have learned that electric field goes from where? Plus to minus. Electric field always go from what? Plus to minus, right? So electric field always go from plus side in outward direction. In outward direction. Clear? So this electric field E vector, right? Suppose this surface I'm taking here. From here, the electric field will pass. The electric field will pass means this will be what? Your it will lead to electric flux for small area. Okay. So this area is, suppose my area vector will be this side. Clear? Fine. Now we're going to find out the actually we're going to prove the electric flux, right? Sorry, Gauss theorem, right? So first we have to find out electric flux for this particular area. Okay. Suppose, what's the formula? Electric flux, you know, right? E, clear, cos theta, right? Now see, what will theta below? This called what? Area vector. Always remember one thing, area vector is always perpendicular to the surface. So this perpendicular surface on this is the surface, right? So area vector and electric field in the same direction. So if area vector and your electric field in the same direction means we can write theta value is 0 degree. So if I have theta value is 0 degree, how much will you get? Cos 0 is how much? Cos 0 is 1. Clear? Cos 0 value is how much? 1. Clear? Now, so we can write E value is how much? Electric field value from Coulomb's law. Remember this value? Clear? Now we're going to find out the, as we said, we find out the electric flux for this particular area only, right? Now we're going to find out total electric flux, total for the full surface. So total, I've told you in the previous video, when you do total, right, what do you do? Integration, right? Clear? So integration, this closed surface, right? So clear? Now say this will remove also the integration. Now, what's the value of surface area of sphere? 4 pi r square, right? Surface area of sphere. So this one cancel. 4 pi cancel. So what's remaining, student? Check properly. So proof one or Gauss law. Clear? Fine. So this is how to prove it? Gauss law. So, but remember one thing, Gauss law can be applied only in closed surface. Some condition is there for Gauss law. Okay, clear? So we'll discuss that one. See, now there is some condition about Gauss law. Okay, see, note, Gauss law is true only for closed. Gauss law is true only for closed surface. Only for closed surface, like 3D surface. As I said, closed surface means 3D surface. Gauss law can be applied. Other surface like 1D, 2D surface, Gauss law cannot be applied. Clear? So number 2 point is total electric flux through any closed surface 0, either if no charge is unclosed. Clear? Either no charge is, suppose this one example. So once here no charge. Suppose here no charge, okay. So if no charge means electric field will not pass, right? So suppose this one here plus charge is there, here no charge, so here flux will be 0, here flux will not be 0, okay, not equal to 0. Clear? Because charge is there, because for electric flux always we need some charge, right? Okay, last point, the closed surface that we choose for application of Gauss law is called Gaussian surface. It's called what? Gaussian surface. Clear? So Gauss law, any surface, suppose if I apply to this surface Gauss law, so this surface will be called Gaussian surface. Clear? So these are some condition for Gauss law. And now we're going to do some application. Application is very important for your exam student. Okay, listen carefully. Clear? Okay, there are 3 applications about your Gauss law. Okay, now the first application, see, application of Gauss law, right? To find an electric field, always remember one thing, Gauss law is applied to find out the electric field, okay, to a long infinitely straight charge conductor. Now see, first, as I said, first try to understand the figure always. Clear? See, this one small one long road, okay, and it has positive charge. Try to understand by like that. First one road is there, it has positive charge, okay. So obviously, you know, positive charge, what they will give electric field this side, this side, this side. Electric field will give or not, but we need to apply Gauss law in this, right? What's the condition of Gauss law? For Gauss law to apply, the surface should be closed. The surface should be closed. This surface is closed? No. So to close the surface, we'll put one cylinder. Clear? Fine. Now this surface is closed or not? Sorry, this surface is closed or no? No. Clear? So simply like that. See, look, this is a figure. So positive charge is there. I close the surface. Clear? I close the charges, right? And this length is L, the cylinder. Now as you know that I told you electric flux will go this any direction, right? But I'm taking only one direction first, then only I'll find out the total flux, right? So this direction electric flux, right? Example, this surface area vector and electric flux in the same direction. So this area will be, as I said before also, you can write A also. In some textbook you'll get A in place of S, same only, okay, don't get confused. So first we have to find out what electric flux for this particular area, right? Small area, then only total electric flux, as we done before. Similar, easy. So what's the formula electric flux? Right? Clear? So now see, area vector always is perpendicular to surface, not area vector and electric field in the same direction. So theta will be your 0 degree. Clear? So cos 0 is how much? Cos 0 is 1. So you'll get, clear, since cos 0 degree is equal to 1. Clear? Fine. Now we'll find the total integration. So total flux. I'll find the total flux. Total flux means what do you do? Integration, right? And it's a closed surface. Clear? So This will be out of integration. Now, so what's the formula of surface area of cylinder? We are using cylinder right here, right? So surface area of cylinder is what? 2 pi RL. So this is equation 1. From Gauss law, what we got? From Gauss law, this one, right? So this is equation 2. So if you combine equation 1 and 2, what we'll get? We will get, clear? Fine. Now, as you know that if you've seen your notebook, there are three types of charge distribution. One is called linear charge distribution, surface charge distribution, and volume. Now see, this linear not, right? As is already mentioned right here. So linear charge distribution, right? This one, right? So what's the formula for linear charge distribution? Lambda by charge by length. So when you use this formula, when you have linear, right, charge distribution. So if you cross multiply, what will you get? Clear? So now see, in place of q charge, we can put this value not. See, I wrote this one here. In place of q, I will write lambda L. So epsilon naught. Clear? So your LL cancel. So what's remaining? E, I can write that. Clear? So 2 pi, right? 2 pi R epsilon naught. So this is the electric field for your infinite long straight charge conductor. Are you clear? Infinite long charge conductor. Is it clear? So similarly, okay, there are again two applications. If it's in your notebook or textbook, it's mentioned there, right? Clear? So in the student, in the next video we'll do the other two application. Okay, please go through and try to practice. Okay, it's very important for your exam. Clear? Okay, thank you.